Okay, welcome. In this video we're going to take a look at a second method of creating an auto joint system. And this second method is going to use the intersect helper in order to cast rays from one particle to the other. Let's bring up MS Paint. So if we have a shape here and a shape here, two particle shapes, and this is its center and center. So what we're going to do is create an intersect system. So we're going to do kind of the same p-search as we did in the first auto joint, where these particles look around, they find each other. But this time they're going to do an intersect where they're going to calculate that direction toward the other particle, and they're going to calculate an intersect ray until it detects that collision on that surface. And then we're going to create a joint at that position. So to do this, we're going to go ahead and start off using a file that we had ended with for the first auto joint system, which is here under videos, under SC. And this one's called auto joint system 1 end. And so what this one does, as you remember, is it averages the positions of the two particles and creates the joint right there in between them, which is fine for simple things like this, but this intersect method is going to give us a kind of a little more flexible method and approach, because a lot of times you do not want the joint to be inside the particle shape. You can get some erratic behavior. So let's go ahead and modify this, get this set up here. Okay, so we know we're going to want to use the intersect, so let's go ahead and drop one of those out here. We're going to control where this joint position is created, so we're going to go ahead and disconnect this average position, and we'll disable that operator so that we don't expect it to be used right now. And you notice that all these particles have jumped into the middle, and this is because they are being given a joint with no position location. So let's go ahead and disable our joint for the moment. Let's see, we've got the joint markers here. Let's go ahead and make another group just to help us out. This one we'll call Intersect Marker. Intersect Marker, most helper groups, we usually like to make them green since they're helpers. And let's go ahead and make those, ticks will be fine. Okay, so we've got all of our particles here, and let's go ahead and take a look. The position that's going to be starting the intersect is going to be the object position. So each of these orange particles is going to be the starting position. Let's go ahead and show their actual center of mass there. Okay, so for the joint between this particle and this particle, it's going to use this position to start. It's going to shoot a ray in that direction. So let's go ahead and get that direction calculation. To do that, it's pretty simple, of course. We just use the distance condition. And remember that in order to get a direction from this particle to the other particle, you're going to kind of want to wire these positions in reverse. So if this is going to be our starting position, we're going to put this in position 2. So position 2 is kind of the start of the vector, and position 1 is the ending point, or the direction that the vector is heading. And then we'll go ahead and feed that direction into our direction there. And then we're going to go ahead and turn on speed as ray length, and that allows us to detect collisions all along the ray as we're going forward. We're going to need to detect the particle shape on which we're calculating that intersection. So let's get the particle shape from the p-search particles that we're looking for. And I think that's pretty much all we need for that. Let's go ahead and let's duplicate this helper rule here. Let's set up that position and the hit, and we're going to go ahead and create some intersect markers wherever we get those intersects. So let's take a look and see. Hey, look at that, we get none. What a surprise. Let's go ahead and see what happened there. So let's measure our distance, because it might be that our distance is just too great. So we'll use the line tool. So from here to the shape, okay, so a distance of about 20. Looks like it's going to come about this far. To actually go all the way to the center of the particle would be about a distance of 30. Let's go ahead and make that distance 30 just because. Okay, now you see we get a whole bunch of green particles being created. Those green particles, of course, are the intersect helpers. Let's turn off that line tool. Okay, and so we are seeing now intersections being cast from all these particles towards other particles. Let's go ahead and get our joint set up. So we'll enable our joint, and because edit on the fly is turned off, all those things jump right in the middle. Let's go ahead and specify that world position to be the hit position of the intersect. And then let's also go ahead and control when that joint is actually created. We'll turn that on if that ray actually hits. But then one more little control we want to do is we want to control when this intersect is turned on. We only want to calculate and attempt that intersect if the number of joints between those two particles right now is 0. So if there are no joints between these two particles that used to be here, if there are no joints, then go ahead and calculate that whole intersect function. So we'll connect that to there. Okay, so now you see our particles here, and then we also see our joint marker here is this little position born, and these are these purple particles with their number. So we get both the green particle for the intersect helper, the purple particle with the number, the PID, is our actual joint marker, showing us where that joint is being created in world space. And so, I mean, that's it as far as setting up an intersect system. It just, as soon as we wire this in here and we detect that shape collision, or that shape intersect, we can go ahead and just create a joint at that location. It's pretty straightforward. But we will take a look at some other things that we can do. Let's go ahead and check the performance of this first. We'll go ahead and play it. So it looks pretty fine. Our joints being created are spherical. Let's go ahead and actually allow more than one joint to be created. Okay, so now you can see that the number of particles has kind of drastically increased, and so this is probably going to double our joints at least. And so if you have a lot more joints, you get much different kind of behavior, which is actually really cool. So using multiple joints, we can really strengthen and kind of shape the behavior of those joints. And remember, they do not all have to be a specific type. You can actually modify that type here on the fly if you wanted to. Set up some kind of condition for when a certain integer should be fed into this type and control it that way. Okay, so let's go ahead and actually modify our objects here and take a look at using some different kinds of shapes. I think what we'll do is we will just go ahead and create a simple kind of dummy shape, something kind of like a boomerang. And extrude that bad boy. And let's center its pivot. Okay, and then here in our where we're creating all of our orange objects there, we're going to go ahead and add a shape operator for the geom instance so that we can use that new shape. Let's go ahead and normalize it to 1. Remember, when using a geom instance, sometimes you can get some performance slowdowns if you're set to original size. So if you normalize it and set it to 1, that's going to be the same as the original size. But for some reason, or at least it used to be the case, that this slowdown occurred, but haven't really noticed lately. So anyway, we'll go ahead and add this custom shape. We'll disable our standard shapes, and we've got a size being applied to those. So let's disable that size. What about our scale? Our scale, it's actually flattening them out. Let's go ahead and disable that too. Okay. So you can see that it's going to actually create the joints at kind of some different locations now, based on that actual object shape. Let's go ahead and see what kind of result we get out of this. Okay, not quite as fun as all of the springy objects that we had before. But remember, our purpose here is to actually look at using intersect with custom shapes and being able to detect the location of those. We might actually get a little, maybe we'll add a little position variation and direction variation in our particles. So what's going to happen here is we're actually going to end up starting to move some of these particles outside of the found radius. Now let's change this auto joint name. This is supposed to be intersect. So they've moved, some of them have moved outside of the 34 units. If we go ahead and increase this, we'll see that start to pick up again. That's interesting. This one does not pick up any joints. We can actually allow, well, it doesn't really make much sense, but you could allow more joints in that kind of case by adjusting this threshold. So kind of a little funky with the custom objects. Probably a poor choice on my part, but you get the idea. Okay, so we're going to go ahead and move on now to the surface sampling method. Before we do that, let's go ahead and just disable our current rule. We're going to leave it on that. Let's change that position variation. Because we kind of like that springy behavior that we get on that flat kind of plane there, like that. Okay, so now we're going to move on to the surface sampling method, where we're going to actually put samples all over these particles, find near pairs, filter out those pairs, and then make those joint connections. Okay, so we'll do that in the next video. We're going to go ahead and save this file out as, I think it's SC, is it 6? Yep. And actually, it's already, I've got a start in there. Let's go ahead and say end. Okay, let's move on.